I have to like, I know what I want to say, but I look up a word.
What's it on?
For what I have to say.
I legit have a thesaurus out when I try.
What do you, what's you ready?
I haven't looked at them.
I'm sorry, people like me.
All right.
She's gonna work on it today though.
So, we're here. We've made it about halfway through the week, right? And by the looks of it, you guys are feeling about as motivated and full of energy as I am this morning. So, it's been a long semester already, but here we are, right? So we will be wrapping up the Equilibrium chapter today. We'll spend a little bit of time just doing a couple of problems, just enough to get you guys mad, and then I'll let you guys go. And then we'll do a couple more problems on Friday there, kind of covering the Le Chatelier's part of it, right? So I always hate to give you guys more practice problems the day that we finish learning something, just because my opinion on the matter, and remember, since it's my opinion, it's the best opinion, right? So my opinion on the matter is that, whenever we learn something, especially in chemistry, we have to let it marinate a little bit, right? So we have to kind of stick it in the back of the fridge and think about it and let it soak in, and then we can come back and approach it the next time here, right? So we have to spend a little bit of time with it. So that's kind of the plan for today. And then we will move on into the acids and bases chunk of the class, and we'll be there for, I think it's 2 or 3 chapters is what it is. So, but we'll be using a lot of the stuff from Equilibrium. Not a lot. We'll be almost exclusively using this stuff from Equilibrium when we're dealing with the acid-base part there, right? So it's got to be something that you guys get familiar with, and we're going to see it over and over and over again, and this might be your least favorite thing ever in the world, and that's fine, but you still have to use it for the upcoming exam and for the upcoming quizzes and that kind of thing, right? So make sure you guys are spending the appropriate amount of time that you guys need to understanding what's going on, right? To working through some of these problems. And there's no mystery to how Gen Chem 2 or how to be successful in Gen Chem 2. I'm just being honest. Right? The mystery is you got to work some practice problems. That's really what it comes down to, right? Understanding what the equations are telling you, understanding what variables are, right? Being able to everyone look at her. She's trying to sneak in very stealthily. So understanding what the different parts of the equations are, that kind of thing, right? And the only way you can get better at that is if you're spending time actively looking about it, actively thinking about it, these kind of things, okay? If there was some shortcut, I would tell you guys about it, okay? If there was some secret, then I would make it known to you, but I'm not holding back Gnostic wisdom from you guys, right? Because I'm contemptuous or something like that, right? So there is no mystery, there is no secret, you just got to do it, right? Even if you don't like it, right? You still got to do it anyway. Why? Want to do well in this class, right? You guys want to get an A? Like, C's okay, Dr. A. You guys want to get through this course is what it is, right? You guys want to get through this course and be able to share your horror story about making it through Gen Chem, the skin of your teeth, right? That kind of thing, right? So, but in any case, all joking aside, right? If you guys do need some help, just come by and see me, right? I'm here to help you guys out, but I can't help you guys after the stuff is due, right? After the exam is over. These kind of things, all right? So just asking you guys again to take some time, right? You guys paid for me to help you out, right? So come get some help if you need it. That's all I'm saying. Okay. All right. Cool. So we were introducing again one of these core ideas out of the Equilibrium chapter with Le Chatelier's principle. And it's important because Le Chatelier's principle is just basically the way that we can start to push the equilibrium and start to change it around real quick. Yeah, what's up?
Is the quiz Friday or Sunday?
I'll make it like due Monday is what it is,
okay.
So you guys have to, I hate to always load you guys up on the same week. You guys have an exam, right? So I'm not that big of a jerk yet, but the older I get, maybe I'll get thrown here. I don't know. So we'll see how it goes, right? Anyway, we're making our way through Le Chatelier's principle and kind of just looking at the how we can influence and push the equilibrium in one direction, right? And we'll talk about a couple different ways, but just to kind of paint the broader picture here about how do we use Le Chatelier's principle. Basically, Le Chatelier's principle is a combination of K's into Q's, kind of the other idea that we've been talking about, right? We stress the equilibrium, and then we have to find the position in the equilibrium, right? AKA, we do something and we have to calculate Q. And then we just calculate that new Q to whatever our K was, and then we can make that assessment that we did previously. That's all we're doing mathematically, right? But conceptually, all we're looking at is, how does whatever we stressed change where we are, right? So the way I approach these problems are not necessarily in the mathematical way, but in just kind of the thinking about what's going on kind of way. And we'll do some problems like this on Friday when we get back to it there, right? And I'll kind of walk you guys through the different kind of approaches that I take. But for what it's worth, let me back up here for just a second. Right? This is kind of the stuff that I keep in mind here, right? This is kind of stuff that I would start to look at when you guys are starting to think a little bit about the Chatelier's principle, right? What are the different stresses and what can it do? Now, I know you guys, or for the most part, I'm always speaking in generalities, not anybody specific, right? For the most part, you guys have a proclivity towards memorizing what happens. If this, then that, and that's fine, right? But understanding why that would be the case, so you guys could explain it. In case you have a professor who likes to ask you questions like, explain your answer, right? Just for instance. So understanding why decreasing a temperature would shift towards or away from an endothermic or exothermic reaction, or these kind of ideas, right, would be important. So that's kind of the approach that I'm going to share with you guys, right? All right, cool. So there's that. I think we talked about the stuff that I kind of had on my mind. So we'll get started with some prayer, and then we'll just kind of work through the rest of this stuff, and we'll see how far it takes us today. But Lord, we just thank you yet again. Lord, we know that we can come before you whenever we want, and Lord, we just pray that you just spark that fire in our hearts, Lord, just to be able to lay our worries and our troubles before you, Lord, just to humble ourselves before you, and just help us to understand, the relationship that we have with you, Lord, that we can just talk with you whenever we want, when our hearts are troubled, when our minds are troubled, and when this world is kind of pulling us in a million different directions, Lord. So we just pray that you give us the strength to make it through this day, Lord, just to give us the wisdom to carry out the task that you have set before us, and just the motivation and the focus to get it done, Lord. And we just pray all this in your name. Amen. All right. So, this is kind of where we got left off, but, kind of just reflecting back. Oh, sorry, there was one more thing I forgot to tell you guys in terms of the recap. For some reason, I accidentally deleted the recordings from Friday, so I'm sad because my fantastic jokes are lost. Right? There's a whole 5 YouTube viewers who will just never see those jokes ever, and it makes me sad. So I'm sorry about that. If you guys, it's not up there. I don't know how it got deleted, but hey, here we go. So anyway, so this is where we kind of ended on Monday there. And so just as a quick point, let me recap this here again. Right, the K is not going to change if we change the pressure or the volume, right? The equilibrium position might change, right? So equilibrium position is just another way that the book says, or that I have in my notes, of just saying Q, right? That's all it is, right? So if we stress the system, then we have to reassess the Q is what it is. And then we compare that Q to the K. Why doesn't K change? Because it's a constant, got it, right? So that's the whole idea there. So if we have a specific reaction, right, where we have N2O4 going to 2NO2, if the volume doubles all concentrations, right, we'll divide by 2, right? If we're increasing the volume, the concentrations get cut in half, that makes sense, right? And then, this is our equilibrium expression, K equals Q, right, which equals products over reactants. I think we got that at this point, right? And then if we go through, and all I'm showing here is reassessing our new value of Q, right? Our new Q is 1/2 the initial concentration. That's what I'm showing, right? Over 1/2 the initial or the equilibrium concentration, right? And we square it, right? So 1/4 over 1/2, we simplify into 1/2. So our new Q is 1/2 of our original QC, right? So what does that mean? Q is less than K, right? So we don't have as much product as we should. Got it? So when Q is less than K, we don't have as much product as we should, so things are gonna shift to the right, right? We're gonna shift to make more product. That's all we're talking about here. You guys with me on this one here? Right? There's a lot of kind of variables and stuff in there, but all we're saying is if I increase, the volume that I have, we can shift to make, or we can shift towards the side where we make more things, okay? So that's all I'm really trying to say here at the end, right? Yeah?
So you put like half in front of it because you said in that example you did double the volume?
Yeah, I just doubled the volume, so in essence I have all the concentrations. That's where
So you put the half.
that's where these come from, right? I have the concentration that I have, right? Half, okay, 1/2, not half. Does that make sense? Okay, what's up?
I'm still lost.
Okay, about what?
When you, like, I saw when you said that you doubled the concentration to have like the open.
I didn't double the concentration.
You didn't double
I
it?
said I have the concentration.
Okay, so you have it.
I
but-
doubled the volume
But why did you double the volume?
because I said this would make the math easy, and I have to pick an example. I could have said I triple the concentration, right? Excuse me, I triple the volume.
Okay.
And then I would, have to divide everything by 3, right? I just picked the number 4 to make a problem, that's all it was,
Oh.
right? Really, the question could have asked, if I increase volume, what happens? That's the generic expression of this,
Okay.
right? If I increase volume, what would happen to my equilibrium, right? So if we try and take these ideas and maybe take away the scary looking math and all these kind of things, so here's what we kind of get to here, right? So there's my equation at the top, the same, or the reaction at the top there with the same one, right? If my volume is doubled, I lower the concentration, right? And I stress or I change the system by making more molecules to get the concentration back to where it was, right? You guys catch what I mean by this? Right? We have an initial concentration. I dilute everything by increasing the volume, if you want to think about it like that, right? So I have to make more to get my concentration back up to where it was. Got it? What's up?
How are you increasing the volume? With the solvent?
We're in the theater of our mind, right? Whatever way you want to increase it, right? If we had a 2-liter reaction flask and I put this into a 4-liter reaction flask, I'd increase the volume.
What if it was liquid?
Okay, so we'll get to an example of that, but how would that change practically?
You would have to dump more of like a physical liquid in there to increase the volume.
It's still a volume?
The
Right?
beaker has a volume, but the liquid is only going to fill as much of the volume as the beaker as there is
Okay.
liquid.
So
Right?
what's the point you're trying to say?
Like to double the volume of a liquid, you have to add more components into it.
I have to add more of my solvent into it, sure.
So would that cause the same thing?
Am I increasing the volume excessively? So how would it be different?
Just making sure it wouldn't be.
No, I'm not trying to be condescending. I'm
No,
just
I
saying,
know.
if this is what I'm asking you guys to think through with this, how would it practically change something? Right? Would it change it? Doesn't matter.
If the volume of the solvent increases, but the volume of the solute doesn't, is that going to also affect this?
Aha, so there's a good question, right? So we'll get to that in just a second, right? But this is what I'm trying to get you guys to think through there also. Yeah, but
What does it mean when you say convert 2 molecules into 1?
so, yeah, right? So what we're doing in this case, convert 1 molecule into 2 here. So where am I getting those numbers from? So one of the big assessments that we have with Chatelier is when we're dealing with these volumes and pressure changes and all these kind of things, we're looking for how many things get made, right? How many things are on each side of the equation. So how many things are on the left-hand side? 1. How many things are on the right-hand side?
2.
How am I getting that? My stoichiometry, my balanced equation, got it? Right? So looking for how much stuff gets made on either side of it's going to be something important to pay attention to. Right? So that's where the 1 and the 2 comes from. They're just looking at the stoichiometry, right? I could say convert 1 mole into 2 or whatever it is, right? 1 thing into 2 things or 2 things into 1 thing, right? So if my pressure is doubled, right? So if my pressure is doubled, it means now I start to squeeze things together more, right? So I'm increasing my pressure. It's like if I decided to give you guys another exam this week, right? Would you guys feel under more pressure? right? Would that stress you? Would you guys shift your equilibrium? Okay, I'm almost stopping now, right? Right? Do you guys get what I'm saying with this? If I increase my pressure, I'm trying to force things closer together, right? So what I want to do is start to decrease that pressure to get back to where I was, right? By dropping out of school or something. No, don't do that. Professor encourages dropping out of school. 1 out of 5. Okay. So, right, do you guys catch what I mean by this? I increase pressure. I want to get back to where I was. So how can I do that? Well, I would shift to where I have less stuff, right? If I decrease the amount of things I have bouncing around in my reaction flask, right, that would decrease my pressure. So I would shift towards where I have less of my stuff. Got it? And it just so happens I have less of my stuff on the reactant side, the left-hand side. You guys with me on this? Everybody following along with this line of thought there? How much math did we do? Well, we compared 2 to 1. But I trust you guys to be able to nail that one each time, right? Does this make sense? We're just trying to get back to where we were, whether it's through pressure or whether it's through concentration. Good?
So the pressure in the products end is increased or doubled?
This is in a flask. We can't just say the one, these aren't in separate flasks, right?
Mm-hmm.
This is, you have a flask, you dump your stuff in there, the reaction goes.
Mm-hmm.
If I increase the pressure, it's gonna shift the equilibrium, right?
Okay.
That's all it's saying. They're not separate, and they're separate molecules, they're in one container, right? So, now let's take a look at the exact same thing, but subtly different, right? Just to kind of get the point across mathematically here. So now if I have this equation, or excuse me, this reaction, right, and I change my pressure and volume, it's not really gonna do anything. Now why would that be? Well, the answer is because of our stoichiometry up there, right? If I have 2 on either side of these things, I have 2 things, then increasing the pressure is not gonna affect anything. So I can't shift to remove any of that, right? And then if we think of concentration, we can go through the same math, right? Here's that equilibrium. We double the volume, right? So we have everything, right? But the math will come out to be exactly the same at the end of it, right? So what does that tell you? That means that if I change my volume in this case, right, then I'm not gonna end up changing anything with my equilibrium, right? You have a question?
What is the N technically stand for?
Mm-hmm.
The delta N, what is?
Change in moles, right? Yep.
Why is N the symbol for number of moles?
Because that's the way it's been. I don't really have a great answer for you. I mean, there's only so many letters that we can use, and lowercase, italicized n is what we chose. So. Good? So what's the difference between this one and the one we just did? Just looking at how many molecules are on either side of our equation, right? Either side of our reaction. And comparing what's going to happen as we change our concentration. And just as a kind of a curiosity, I guess, or this is something that I've seen mentioned in a couple of versions of different textbooks. So if we add an inert gas, okay, so what do we mean by this? So if we just add something into our reaction that actually doesn't participate in the reaction, right? That's all it's really talking about here, right? The total pressure increases, right? The volume does not change, nor does the amount of reactants or products, and the concentrations don't change, right? So it's not going to change anything in terms of our equilibrium here is what it is, right? So just kind of, I don't know why some books want to talk about this stuff, but this is kind of an odd one out there, but I think practically, or just as a little bit of an aside here, so when you write just a step back, so when you write a textbook, right, for general chemistry, how many of you guys are taking general chemistry across the US this semester? The answer is thousands, right? Thousands of you guys are, right? So we're talking to you guys, we're talking engineers, we're talking to biology majors, we're talking to all these different types of students who are walking through this. So when you write a book that has to, teach thousands of students, sometimes we have to add things like this in there. And so this probably is, geared a little bit more towards our chemical engineer friends is what it is. And just how can you practically increase the pressure of a reaction, right? But anyway, for our sake, it's just kind of one of these interesting asides, just something to think about a little bit is all it really comes down to, right? All right, so now we get to the other question that was asked earlier here, right? So, you know, at the top, equilibrium is not changed by solvent addition or removal, but again, we could change where we are in our equilibrium position Q, right? Yeah.
I have a completely off-topic question.
Okay, let's say it then, okay? So, if we have, again, if we write our expression of K, right? We can calculate K or a given K, that kind of stuff. If the volume is double, what happens? Right, the concentration of every species is halved. We get half of Kc again, which means Q, right? We have to shift to make more of our product, right? Which is the exact same as what we saw under the gaseous conditions, right? So practically speaking, to answer your question there, you know, how's adding more water or solvent or whatever going to change this? The answer is, we're just doing the same thing, right? If we're talking about increasing volume, we're just giving the molecules more space to roam, is what it is. Right? It's like if we took this class and we suddenly started to teach in the black box theater, right? You guys would all spread out a little bit more, right? Because you have a little bit more area to roam, okay? It's the same thing with these molecules here, right? And then the equilibrium is going to shift, right? So we can get back to the concentration that we started before, right? Before we change the volume there. That's all it comes down to. Good? Make sense? Why does my K look like that? Right? Did I leave something off? Crap, I made a typo, right? Oh, okay, I guess I did. All right, oh, we'll see. I'm kidding, it's not a typo, but ask me. Do you guys see what I'm talking about there?
No?
What's the expression for K? Products over reactants, right? What are my products?
Oh, 'cause it's a liquid.
Right? What are my reactants? So why don't I have one thing on the bottom? Aha, right? Don't forget your liquid, right? Concentration of water is way too high for any practical effects there, right? Cool. All right. So now we get a little bit into something that we have been kind of hinting at behind the scenes here and talking about and all these kind of things. A change in temperature does change our K, right? So here's our one thing that can change our K. But it's not just increased temperature, increased K, it depends on what the reaction is. Got it? So here's a reaction we've seen for the umpteenth time now. Nitrogen plus oxygen makes NO, right? I don't know why we tend to pick these. I guess maybe they're just simplistic. What's delta H? Enthalpy, right? Which is just a measure of a form of energy, right? So I have this reaction. I give you guys a delta H of plus 180.5. What does that mean?
Endothermic.
It's endothermic. What does that mean?
It's taking in energy to do the process.
Right? So I need to, I need to add energy to make this go is kind of what it is, right? It absorbs energy as you go through it. So it's important to pay attention to whether a reaction is exothermic or endothermic, because that's what's going to end up changing, right? That's what's going to end up changing the equilibrium. Excuse me, how temperature is going to end up changing the equilibrium. So here's some values for this, right? At essentially room temperature here, right? We have an equilibrium constant of 10 to the negative 31. What does that mean? To the negative 31?
Really
Yeah, nothing, right? This reaction is essentially not doing anything. Right now, that makes sense. Why? Do we have nitrogen in the air around us? Yeah. Do we have oxygen? Yeah. Do we have a lot of nitrogen monoxide around here? Well, we certainly hope not, right? Okay. But as I start to increase temperature, what happens to my K? It gets bigger and bigger and bigger and bigger and bigger, right? So what is this telling you then? I have an endothermic reaction and I increase temperature. Right? I have an endothermic reaction and I increase temperature. What's it doing to my equilibrium? It's shifting it towards my
It's making it
It's making, what do you mean easier for the reaction to happen? Which reaction?
The products to be formed.
It's making it easier for the products to get formed, right? So hang on, I'll get to you guys' question in a second, right? So what does that mean? So let's think about this for just a second. I have an endothermic reaction, right? So the way I look at this is that if I have an endothermic reaction, that means I have to have heat over here, right? As part of my products. You guys with me on that? Because an endothermic reaction means I absorb energy, right? But we don't really write equations with a negative value in there, right? In terms of like NO2 minus energy, right? You guys get what I mean with this? Right? So I have to add heat into that side of the reaction. The other way to think about this is if this reaction is endothermic, the other reaction is what? Exothermic. So heat is a product over here, got it? So depending on which way you look at it. You guys with me on this? Yes? Good? Cool. What's up? I know both of you guys have questions.
So if the atmosphere of the Earth was like suddenly heated to like 300 degrees or 3,000 degrees Kelvin, the air would just become toxic?
Probably a lot worse things than that would happen. Are you saying what, different things start to react in the atmosphere? Sure. What's up?
So the equilibrium constant is a ratio of the rate of products over the rate of reactants, right?
Yeah.
So why would a small k mean, isn't k like a?
Mathematically, what does this mean? It's just a small number, right?
Yes.
Yeah, right? So we have a numerator over denominator. If I want to make a really, really, really small number, what do? 1 divided by 1 billion is equal to what, right? A really small number. 1 billion divided by 1 is equal to what? A really big number.
So
Got
the
it?
products, it's not making that many products in comparison or proportion to the reactants.
That's what it means.
Oh,
Yep, your reactants are in a much higher concentration.
okay.
You guys with me on this? So now let's see what Le Chatelier says. Now as I add more stuff on this side of my equation, what happens? I push towards what? That side over here. You guys with me on this? I change my balance, so, or my scale, so I have to adjust to get to the other side. Good. Just as if I removed heat from this reaction, what would happen? Well, the reverse reaction would help then, right? The reverse reaction would be favored. Got it? If I suddenly cooled this down, if I removed heat, then I would shift back to this direction there. Does that make sense? Let's follow along with this. Right? We add things to one side, it shifts to the other. We remove things from one side, it shifts to fill that back in. Right? It's like digging a hole at the beach, right? The sand keeps trying to fill it in, right? Keeps trying to collapse in on it, right? As you remove things out, things want to fill it back in. Good? I guess I want to go to the beach. I don't know why I was thinking about this stuff. All right, there it is. So if we take all those ideas, right, I think we kind of put those into word form here, right? So if temperatures increase, we minimize by removing heat is another way of looking at it. The forward reaction is endothermic. Reaction shifts forward to remove that heat, right? It's the other way of looking at it. Temperature is reduced. The reverse reaction is exothermic, so we equilibrium shifts in reverse to release that heat, right? So like I said, the way I look at this is when I read an endothermic versus exothermic, I just add plus heat to whatever side of the equation is appropriate, right? And then we can make that assessment. So just as I guess to kind of put a final touch on this here, right? So if we have an exothermic reaction, our Kc decreases, our equilibrium constant decreases as temperature increases, right? less product favored at higher temperature, right? And the opposite is true. Again, that's just the third way of saying the exact same thing that we have. So it's important when we're looking at how to design a reaction, you know, whether we actually do need to heat it, or whether we can just let it run at room temperature, or whether we need to cool it down, that kind of thing. Right? And that's gonna help us kind of shift our equilibrium. Yep, and that's the end of that, right? Cool. Any questions before we do a couple practice problems then? Yep.
Can you go over the difference in Q and K again?
In what way? What?
Aren't they the same formula for both?
They're the same formula. Now Q is basically our snapshot, right? So we dump some stuff together. A certain amount of time has to elapse before we get to equilibrium, right? Our Q is just our snapshot along the way. And what we do is we calculate Q, which is like what you said there, right? It's the exact same mathematical expression as K, right? But we compare Q and K to see how close or how far or are we at equilibrium, right?
So how would Q change if you change the pressure to volume, but the K doesn't?
Because K is a constant, right? Equilibrium constant is a constant. The only thing that changes that is temperature. I'm trying to get back to the, right? So this is kind of the visualization of what Q and K are, right? We do something to our reaction to knock us away from equilibrium, right? And then we can take a snapshot with Q and to see which direction we're gonna go, forward or backwards, to get back to our equilibrium.
So Q always tries to get to K?
Well, equilibrium will always be established. That's the rules of the universe, right? Brain hurting a little. It's just one of those things. Yeah, I mean, it's maybe a little bit hard to conceptualize, right? And I think I know what you're asking, right? But for our purposes, to make life a little bit easier, right? K is a constant. Everything wants to get to K, right? Everything will get to K. It just takes time, right?
So what is Q exactly?
In what way? What do you mean?
It can predict the direction.
Mm-hmm. Yeah, I mean, I think the book calls it the equilibrium position is what it is, right?
So Q would never be constant, or like would it always?
Q can be equal to K, right? But it's not necessarily a constant, right? Good. Brain hurting? Okay. Let's start off with something a little bit straightforward then. Cool. All right. One of the most important things to be able to do from this chapter, writing some K's. answer is, what's the concentration of water? Pure water. Concentration is concentration is water. If you can answer that, then you can answer why. Somebody think about that. Write down that question. What's the concentration of water? Pure solids, and pure liquids, they're not part of the equilibrium expression. Because their concentration is not going to change. One button gets caught on the computer, perfect, alright. After you know that you that's the one shot. Oh, I don't see anything. You're right. All right. Any K in terms of equilibrium expression, right, is always what? Products over reactants. The concentration of the products over the reactants raised to their coefficients. Got it? The only thing we leave out are pure liquids and pure solids. So taking, or let me just change colors here, I guess. Taking into account any S's or L's along the way, right? Good? For the majority of the problems that come out of this chapter, and I mean, you know, the practice problems, not like the emotional problems, you're gonna have to start by writing an expression of K, right? That's all it is. So now we have written K. What does this mean? This is an equation now that has 3 parts to it, right?
Wait, yeah, you.
Did I mess something up?
Yeah.
Oh, sorry, I reversed this here, excuse me. I got a little ahead of myself there. Good catch. Suddenly, K changes, all right. Remember everything you learned? Throw it out. Okay. So, what does this mean? Now I have 3 parts of an equation, so what do you need information for? At least 2 of those, right, to be able to figure out the other one. Got it? That's all it is. Okay? I've told you, I've shared this with you guys before. I am no genius when it comes to math. The only trick that I found that works for me is when I see an equation, I sit there and have to explain it to myself in English, right? What is this telling me, right? I need a concentration for CO2. I need a concentration for CO. And if I divide those 2 or make a ratio of those 2, then I will get an expression, right? That is my equilibrium constant. That's all it means, okay? Talk yourself through it. Remember, math is just another language, right? It's a language that, and just like any of you guys who've learned another language before, what's the secret? You gotta practice it, right? There is no trick. If you guys know of a trick to learn another language, please come tell me. Okay? I got stuck on Italian. I always got confused in my brain, so yeah.
This might be stupid, but like it seems like super like similar to like the rate laws and stuff, but just like a little bit different. Like, how are they connected and like
Yeah. So just to that wasn't stupid.
okay.
Right? So there it is, right? So if you take a look at the beginning of the notes, I kind of walk you through how these 2 things are related there. Got it? And we can set up why this stuff comes out to be a constant and these kind of things. Right? So if we have that same reaction we see everywhere apparently, right? We can write a rate law for the forward and the reverse, right? And then since we know that the forward and the reverse rates have to be the same at equilibrium, right, at equilibrium, then we can just set up the ratio and this becomes our constant there is what it is. Got it?
But couldn't we like not use the stoichiometry for the rate laws? But then is that not what's happening?
Right, so so how do we know that here, right? So there are a couple of assumptions that we have to make. Now your question is really saying, how do we know that we can use the stoichiometry in the equilibrium expression? And the answer is, I can show you the derivation for it. But I have to look it up first and then memorize it, and then I can impress you with my knowledge. Because I don't remember it. It comes down to a different part that we're going to learn later on this semester too. Right, and the short answer is thermodynamics, but it's not stuff that we've learned yet, right? So there is a proof, it is a good observation, not a dumb question at all. It's an important question, like, hey, wait a minute, you know, we just said don't use that when we're doing rates, okay? So, a very, very, very good question, okay? I was hoping it was gonna be dumb. I was just waiting. I'm feeling snarky. All right. So, let's say now that we have some nitrogen gas, and hydrogen gas, and they combine to form ammonia. Oh, oops, not ammonia. Try that one more time. Which is NH3, which is a gas, right? So assume we have a reaction at 472 degrees Celsius. And at that temperature, we found that we had 7.38 atmospheres of H2, okay? 2.46 atmospheres of N2, and 0.16, try that one more time, 0.166 atmospheres of ammonia, okay? What is our KP? Okay. So we have a reaction. We ran it at a certain temperature, and we found some pressures, right? So what's KP? would you need them?
I don't know, it has to have like all the cookies. I don't know, I'm just trying to show you what KP is, I don't know.
Ah, that's the question, right? That's the question. Now, that equation is how we relate Kp to Kc.
Well, you can find KC. Oh, we don't have a number for it, so.
Got it?
Yeah.
So how could you find it? I'd have to give you more information and ask the question a different way, right? So what is Kp? What is our mathematical expression for Kp? It's what? Products over reactants, but not in concentrations, but in pressures, got it? So is Kp any different from Kc mathematically? No. Can we relate the two? Yes, but we have to use that Kp equals Kc times RT delta N, right? That thing there. Got it? But on the surface, right? It's just another expression of K.
Is that derived from the ideal gas law? The relation of Kc
Yes.
and Kc?
Yep. Where was it? There it is, right? Amy, the relationship comes from there, right? So there's our expression for Kp, right? All we're doing is in units of pressure. We can relate the two, right? And then don't forget, if I do ask you to relate the two, the delta N just comes from the difference in the amount of the stoichiometry, right? Good? So, pragmatically speaking, what does me telling you the temperature here do? Nothing, right? Although it is useful in a sense because what? If I said something about changing temperature, right, then we'd have to change the equilibrium and that kind of thing, right? So a lot of the assumptions that get made with these types of products is that they'll either give you a temperature or they'll say it was run at a constant temperature. Got it? But knowing when that's important and when that's not important is good to understand, right? Now, what's the other bit of information that you guys need to do before you get cracking on this one? Well, N2 as a gas, right, plus H2 as a gas goes to make ammonia as a gas, right? So we write an equation and then we have to balance the equation. Don't forget to go through and balance your equations. Got it? Yep.
We were asked about Kc changing temperature, would we have to use?
That's a very complex, right? Because we'd have to calculate Kp related to Kc and then analyze how that would affect the temperature. And I have to give you a lot of information about it, right? That sounds like a great question. Thank you, Andy. I'm gonna go write a 5 questions that take you guys 5 hours to do, right? No, that becomes very complex is what it is, right? It's a good question. Right, so we have to balance this, right? So what do we need? 3 and 2, right? If you don't balance the equation, what happens to your math? Right?
I went for golf.
So Kp is equal to the pressure of ammonia squared, right, over the pressure of N2 times the pressure of H2 cubed. So 0.166 squared, right? 2.46 and 7, sorry, got the wrong number there. 7.38 cubed. Good? And if I did my math, I got 2.79 times 10 to the minus 5. Good? What does that mean? Something times 10 to the minus 5. Big number, small number? Small. What's favored, products or reactants? Reactants, got it? Right, so there's not a lot of our products formed at this temperature, right? Now we could talk here, we'll come back probably on Wednesday and say what happens if we increased pressure here, right? What happens if we decreased pressure here? What if I removed ammonia from the solution or from the reaction, that kind of thing, right? Yeah.
Practically speaking, I don't understand how pressure wouldn't affect the rate of a reaction. Like,
I didn't say that.
well,
Nobody
equilibrium.
said that. What are you asking?
P doesn't, so, am I right, that P doesn't, affect the equilibrium, and that's why we can.
No, that's not true at all. That's in fact, that's in your notes. Pressure, if you change pressure, you're gonna change the equilibrium position. You're not gonna change the equilibrium constant,
That would make sense.
right?
What do you mean when you say that equilibrium, position?
Q.
But like, what is, I don't even know what that concept is.
This is what I'm talking about. We start a reaction, we're going along, we reach equilibrium, right? An area where concentrations don't change, okay? I stress it in some way, right? And you'll notice there's some time before I get back to equilibrium. This green area is my equilibrium, right? That's where we're getting back to equilibrium. Got it? So here's where Q is not equal to K. Here's where Q is equal to K. Right, here's where Q is not equal to K, right? That's what I mean by my position. If you want to think about a graphic like this, I'm somewhere along that line. I take a snapshot of that line, I'm either at K or I'm not. And then I have to figure out which way to go. What's up?
And is that in different equilibrium?
No, equilibrium's a constant.
It's out on the graphics.
The concentrations change, right? I'm not disagreeing with that. But the K is constant. Right? The ratio of the two. Right? Alright. Time for everyone's favorite here. Oh no, never mind. We got one more easy one and then I'll make you guys miserable. Alright. So a reaction has 1 times 10 to the minus 3 molar H2 and 2 times 10 to the minus 3 molar N2. Oops, excuse me, sorry, I2. At 448 degrees C. So at equilibrium, concentrations, the concentration of HI is equal to 1.87 times 10 to the minus 3 molar. What is Kc? H2 92 to make H1 gas. Right.
When modeling these kind of problems, and as far as like determining whether to be Q or K, how do we know? I understand that K is when it's in equilibrium, Q
Yep.
is when it's not.
Yep.
But for the problems we're used to, when we see, we'll just say it's not at equilibrium.
Probably, right? If I ask you about Q, I have to give you information about K. Otherwise, because the only purpose for Q is to compare it to K.
Okay.
Does that make sense? And so I have to give you information about something about the equilibrium.
That makes sense. Well, could I just compare the products concentrations over the reactants concentrations, even though it's not in equilibrium, and get Q?
Well, that's essentially what you're doing when you get Q, but that's just a number, right? 5. Well, 5 what, right?
Okay,
5 apples, sounds good, right? You know,
I see.
5 bonus points, sounds great, right? Right? So you have to say what you're comparing it to, what does that mean, right? I don't know, I prefer 5 apples, but not red apples. Green apples.
Sour.
Give me some good old sour green apples. Fantastic. Go along with my bitter personality, all right?
What's your last name? You look like my brother does. Reese Orthodontics.
Careful, guys. You start a reaction, right? A reaction at that temperature has those concentrations. At equilibrium, I have that. Those aren't equilibrium concentrations of H2 and I2. That'd be too easy, wouldn't it?
Then how the fuck are we supposed to figure that out?
I don't know, if only your jerk professor had worked a problem just like this, that's already in the notes. Putting strong emphasis on a new mathematical organizational technique. It would be called ice tables. Right?
Oh, rude.
In my defense, that was the day I was.
You skipped class, is that what you're admitting?
Yeah,
You're recorded, just so you know.
I know.
I'll send it to the president.
But that was the day that the recording got deleted, so.
Should have been in class, what can I say? Ice table is what you set up
No,
when you have your
I see.
initial.
Okay.
Your initial, sorry, I misunderstood you there, yeah. Your initial, what changes as you get to equilibrium, ICE. We have initial information about our H2 and our I2, right? We have equilibrium information about HI. So we gotta figure out what the change is, right? To figure out our equilibrium concentrations of H2 and I2.
So when you Google ice table, the first video that comes up is actually one for this exact problem.
Probably just a video of somebody crying for 10 minutes.
It might be. I'm not actually watching the video, I'm just looking at the thumbnail of it, because it's like,
You guys see this? So this is the information that we're given to begin with, right? We have our initial concentrations of H2 and I2. How much of our HI do we have at the beginning? Nothing, right? We mix the two together, something changes here, and we end up making that much of our product. Got it? So what goes on here then? What has to be our change? What has to be our change for HI?
1.87.
Right? It has to be this, right? Because if we start at 0 and we get to this, then guess what this has to be? Plus 1.87. Got it? So this is plus 1.87 times 10 to the minus 3. Good. Now what? If I make this much H2, how much of these get consumed along the way?
Or X.
Half of it, right? How do we know half? 2 for every 2 of these, right? It takes 1 of those. So if I have an amount here, if I have 1.87 apples, right? Then how much of this? That's half of it, right? You guys with me? Everybody with me on this one? Stoichiometry, balanced reaction, very important. So this is minus 0.935 times 10 to the minus 3, right? Just to keep the scale the same. You guys could say 9.35 times 10 to the minus 4 too, right? Doesn't matter, either way it's the same. Good. So now I minus C gets us to E. 0.067 times 10 to the minus 3 and 1.065. Good? Do what? This was information I was given. If I know I started out with 0, then I got my change for this. The change here is related to these two by stoichiometry, right? That's given information up there, right? Yep. Yep.
Do you always add the change, or the initial to the change?
Like I said, the ICE table is just an organizational tool, right? Now can you guys go through and figure out the rest of it, right? Now that we have our equilibrium concentrations for everything, then we just need to generate our equilibrium expression, plug it in, get the numbers, right? And just for what it's worth, since we're kind of winding down on time, I got Kc equal to about 51 is what it was.
Thank you, Doc.
All right, guys. I will see you guys
Possible.
on Friday. We'll do a couple more practice problems. One quick second, let me just turn this off.